For problem 4, we are given a certain test point charge of 2 nanocoulombs that is experiencing a force, and if we look at the relation between electric field and force, we know that the force is the charge times the electric field. So the electric field itself is going to be the force divided by the charge. And we're given that the force is 8.0 times 10 to the negative 4 newtons, pointing in the J direction. And the charge is 2 nanos, so 2.0 times 10 to the minus 9th coulombs, or a positive 4.0 times 10 to the 5th Newton per coulomb. And the electric field will also be in the positive y direction in this case. For part B, we're told now there's a force on a negative 4 nanocoulomb instead, based on this electric field. What is the force due to this electric field on a different charge? So we can say that the force in this case, I should have put vector notation. So part A is Q times the electric field at that location. So this is now a negative 4.0 times 10 to the minus 9th coulombs. The electric field is what we just found, 4.0 times 10 to the 5th Newton coulomb, in the j hat direction. And if we multiply this, we get 1.6 times 10 to the negative 3rd newtons, and this force is in the negative j direction, if we want to think of it that way. And now it's part C says, imagine now that you have a force that is equivalent to this negative 1.6 times 10 to the negative 3rd newtons placed on where the negative 4 nanocoulomb charge is, and there's another test charge that experiences the same force. What is that second charge? Well, we know that the magnitude of the force is the constant times charge 1, charge 2 over the distance between them squared. So this means that if we assume that charge 1 is the unknown, then we can say that Q1 is F times R12 squared over KQ2, and we have all of these values. Since we're taking magnitude, we don't care about the negative value of the force, so we can say this is 1.6 times 10 to the minus 3rd Newton. Notice I didn't include the direction. It's placed 3 centimeters away, so 0.03 meters quantity squared. K again is our constant, 8.99 times 10 to the 9th Newton meter squared per coulomb squared, times the second charge, again just magnitude, is 4.0 times 10 to the negative 9 coulomb. You do a quick check of the units, the newtons cancel, the meters squared cancel, and one of the coulombs cancels one of the squares, and you get 4.0 times 10 to the negative 10 coulombs, since we started the problem with nanocoulombs, we will change this to nanocoulombs, or say that